So welcome everyone to, I guess, Danny was keeping track. So the fifth session for these workshops, hackathons, where we can hopefully share with you something that's useful on analyzing mass spec data. And so today's session, along with tomorrow, is learning how to do feature finding with MZmine2, and then taking that to the next step with feature-based molecular networking at GNPS. So I actually didn't do anything. The people who should be getting all the credit for all the hard work are Danny and Allegra, who are going to show you and walk you through all of this. Again, what we encourage is active questions. So go ahead and throw them in chat against everybody, and then we'll take it in turn, and we'll leave plenty of time at the end for kind of more detailed discussion. And again, it's a brand new world for analyzing mass spec. So this is one way to do it. It's not, the definitive way to do it. So suggestions and comments and feedback is very welcome, so we can improve as a community. So anyway, I guess my name is Ming, but it doesn't really matter. So without any further ado, one thing, we have 135 people. So thank you all. That's doubled what we usually have. So apparently it's an exciting topic. Without further ado, I'm going to hand it over to Danny, and he'll get us all started.
Yeah, also, if there are any questions, just feel free to use the chat or unmute yourself, but keep yourself muted. The way to unmute yourself is just hit the spacebar.
All right, thanks Ming, and thanks Peter and Allegra for doing this together. It's really exciting. So yeah, my name is Daniel, and I just want to give you a very brief recap of molecular networking, and then talk a little bit about the principle of feature-based molecular networking. And then Allegra is gonna show you the example data set we're gonna deal with today in a hands-on tutorial, before we then go through a step-to-step tutorial for the pre-processing with MZmine. And that's all we want to do today. We will have a breakout room with questions afterwards. And then tomorrow, we're gonna take those files we pre-processed today and submit them to the actual feature-based molecular networking job, and then visualize the data in Cytoscape. So yeah, let me quickly start sharing my Was there a question? All right, I hope everybody can see this now. So yeah, I hope you attended the other classical molecular networking job 2 weeks ago. And for those of you who haven't, what the basic principle of molecular networking is that we take all MS2 spectra of a given data set, and then we cluster identical spectra together in so-called clusters, and then we display those clusters depending on their spectral similarity inside of a molecular network. So yeah, basically on the left you have the input data from LCMS, so you have MS1 and MS2, but then you take only the MS2s and collapse the identical spectra in clusters and then display them here as a network. So now when we think about this, when we look at a particular example, then we are kind of limited to only information where a precursor was abundant enough to trigger an MS2 spectra, right? Because in classical molecular networking, we don't make use of MS1 information. So for example, here we have 3 peaks, and now in the first example, basically this dashed line here is the threshold for an MS spectra to be triggered, and in all of those 3 cases, the intensity was above the threshold and an MS2 spectra was triggered. And now we can basically display this in a molecular network. So if we now want to compare sample A to sample B, in sample B we had the case that actually that third green peak was below the threshold of the MS2 trigger. And hence, when we now look at this molecular network and think about relative quantification and spectral counts, then you will see that that green peak here does not contribute to that 700 node here. And that is like one of like the like fundamental problems if you only have MS2 level information in your molecular network. Besides that, maybe also isomers don't get resolved. So the idea now for feature-based molecular networking would be that we actually get the quantitative information from an MS1 peak integration and have a more accurate quantitative representation of that information inside of a molecular network. And how we do this is that we simply take all MS1 spectra from an experimental data set, and then we pick like the abundant peaks out of this information and construct extracted ion chromatograms, and then check whether during one of those time windows from the extracted ion chromatograms, an MS2 spectra was triggered. And then we assign those to those peaks. And then we can align those extracted ion chromatograms between multiple samples and kind of like get a relative quantitative output. And there are many feature finding tools out there that basically support that type of like data analysis. And what we had to do for feature-based molecular networking was just to interface that with our infrastructure. And the tool I want to talk about today is basically MZmine, where we do that pre-processing to then create first like a list of extracted ion chromatograms and consensus MS2 spectra that then will be submitted for GNPS, where this experimental spectra will be first searched against the library and then also compared to each other to then construct a molecular network based on their spectral similarity. And then for each of those nodes, we have basically library annotations, and we can propagate this to, I don't know, lipids, amino acids, peptides, and so on. And we also have the extracted ion chromatograms, which gives us the quantitative estimate. So this basically brings together feature finding tools, which are widely applied in the metabolomics community, as well as molecular networking. So we have extensive documentation, besides like plenty of workshops we're doing, such as this Zoom workshop right now. You can go online and read through that, just as a basically backup. So in any case, if you get lost, like please feel free to visit our documentation page and go through that. That also includes video tutorials, and I'm sure we're probably gonna deposit a recording of today's workshop there as well. So now Allegra, I think, is gonna talk briefly about the actual data set we're gonna work with today.
Yeah, so I guess, Daniel, we can continue just using your share screen, and I'll just indicate when I want you to advance the slide. Does that sound good?
Sure, sounds great.
Okay, great. So hi, everyone. I'm Allegra, and I'm also a postdoc in Peter's lab. So today I'll introduce the data set that we'll be investigating in our hands-on portion of the tutorial. And so this data set actually is a data set that we ran on E. coli Nissl culture extracts. And we ran this data set on the Q-Exactive mass spec. And we were interested in investigating which siderophores or iron binding molecules were actually present in these cultures, which were produced by the organism. And so in this experiment that we did, we were additionally interested in developing new technologies to actually allow us to not only find known or previously characterized siderophores, but actually to start to find new and uncharacterized siderophores in data sets such as this one, and then more complex data sets as well. And so in this workshop, and then in the next two workshops following, we'll sort of take you through like how we actually did these experiments and kind of the new technologies that we've developed. And if you're interested in understanding this data set, in addition to the technology in general, I'd encourage you to look at this preprint on the bioarchives, because it kind of goes through what we're going to be discussing today. And then the cool thing is that all of us together are essentially going to be doing what we did in this paper to discover some new siderophores. And so I would encourage you to not only come to this workshop, but to also come tomorrow and then next week, because then you'll get a really full picture of feature finding and a new technology that we call ion identity networking. Next slide, please. Okay, so as I said, this data set is from culture extracts from E. coli Nissl. And so in this data set, we have culture extracts, but we also, but in addition to those extracts, we've also done something else. So we've actually sort of modified our mass spec setup in a way that allows us to start to find new metal binding molecules. And so what we've actually done is, instead of running our experiment using kind of standard mass spec conditions, we've actually now changed our conditions. And so now we're doing what we call native metabolomics. And so what this entails is actually changing the pH of our experiment. So typically we run mass spec at low pH, but now what we're doing is, as you can see in the picture, we're running our sample through the column, and then we're actually raising the pH by the introduction of either a buffer or a base to some neutral and potentially more physiologically relevant level. And so we hypothesized that by raising the pH, if we actually then infuse in a metal salt after the chromatography step, then we can actually have our metal binding compounds kind of poised to bind a metal that we'd infuse. And so half of the samples that we'll be looking at actually include this post chromatography infusion of iron salt. And so for this data set, it was really important actually that we used feature-based molecular networking. And this is because we're going to be focusing on mass deltas between unbound compound and then iron bound compound. And so for that, we'd actually have to be looking at the MS1 level. So next slide, please. And one reason for this is because unbound and metal bound complexes actually have very different MS2 spectra, as you can see in this first example, which shows unbound and metal bound MS2s for the siderophore Yersinia-bactin. Okay, but so for this workshop today, and then for the next two workshops, we're going to be doing some tasks. And so really the goal of all of this processing that we're going to be doing today and tomorrow is to first identify ionophores, potentially Yersinia-bactin, but maybe some others. And then additionally, we'll try to look for different isoforms and then try to differentiate between unbound and bound. And so this just shows an example of how we actually have two different diastereomers of one compound of interest. And then we'll actually see how feature-based molecular networking can actually assist us in that. So next slide, please. So now for the fun hands-on portion. Okay, so we asked you guys to download those 6 files before coming, but just in case, I saw a few questions on the chat. I think there may have been some difficulty with that. So we'll walk everyone through this
Could we get like an overview who downloaded the data and has everything ready? I don't know if people are aware with familiar with like giving thumbs up on Zoom. But if you have like your data, there's actually like a button so we can like see it in like the table overview. That might be good for direct feedback. Okay, I see 1, 2. Okay, Tom got it. Roger got it. Awesome. Okay, all the others, you don't have your data downloaded yet? Okay. So great that Allegra is going to walk you through again to how to
Yeah.
download it.
Okay, yeah. So yeah, now everyone, the first thing we'll want to do is go to Massive. And so that is basically just massive.ucsd.edu, as you can see at the very lowest part of the slide. So I can also send that out to everyone in the chat. Okay, so assuming everyone is now on the Massive website, you can click on Massive Datasets, which is the pink boxed button on the slide. And so next slide, please, Daniel. Oh, can you go back one slide, please? Thank you. Okay, so once you have clicked on that button, then you should see the page that looks like this. And then we can search for our data set of interest. And so you can really search anything in the title portion of this table, but it's easiest if we have the Massive accession number to just search that. And so I encourage you to type in this MSV 000084628 into that box, and then you should see this GNPS Metal Edition E. coli Nissl dataset for workshop that should pop up. And again, if anyone is having troubles, I encourage you to reach out to the chat and we can help you. If not, we'll continue along. So next slide, please. Okay, so once you click, oh, okay, someone needs some help. Okay, Hum needs help. So, okay, so at this point, we should see this page pop up, and then we can actually click on this FTP download here. Okay, and then next slide. So once we, oh, back one slide. So once we click on that, then we should actually start to see.
So we have a message from Hum. I don't have it. Please wait.
Okay. Okay, I guess we can just wait for everyone to catch up unless there are specific questions.
You may have to go back. Is there anybody who wants to follow that could not follow it? If so, we can go back to make sure that you're on the same page.
Oh, okay. Seems like we're good.
Great.
Cool, thank you. Okay, great. So at this point then, once we click on that FTP download, we'll actually get to the folders that contain our files of interest. And so we'll click first on this peak folder, and then that'll bring up the MZML files that we'll be using for this workshop. And so you can then download these 6 files that are boxed here. And so if everyone could please do that at this point, these will be the files that we'll actually be processing in MZmine. So yeah, we'll give you a minute or two to get them downloaded, and then Daniel will take over. And And so again, if anyone is having trouble, please just reach out on the chat. And then as we go through the processing of these files, then if you have troubles at any stage, can you just, again, send a message on the chat, and we'll respond to your message, or we'll bring up the question to the group if it's sort of relevant for everyone. So yeah, I'll give the floor back to Daniel.
All right. Thanks, Allegra. I just saw that there was a question if there is a good way to download them all together. And the short answer is yes. So you can either use basically that FTP link and connect you through an FTP client, such as WinSCP, or for the Windows user, you can just copy and paste that entire link into your Explorer. So I'm just going to stop sharing for a second and show you that trick, because I think that makes your life definitely easier. So let me share it back. So if you're on Massive and you basically browse public available data sets, so, and ours is in there, right? So it's Metal Edition, and yeah. So then you can see there would be one here, which is like a later version. Then I can simply take this link here, that FTP download link, and copy this, and then just go to my Explorer and paste this in here. And then in theory, that folder structure should also be appearing on my computer. So, and that makes especially sense when you have like large data sets. I mean, for this one, I think the way Allegra showed you is totally legit, because it's just 6 files. But if it's like 200, then obviously you want to have this in a faster fashion. I'm not sure for Linux or Mac, but then you can use like an FTP client such as WinSCP. All of that is also described in the GNPS documentation. So yeah, if you kind of like lost it here and you're still struggling, then I would encourage you to yeah, like read the documentation from GNPS. And yeah, just do the step-by-step as Allegra just showed you. All right. Okay, who does not have that data on their computer right now? Do you want to indicate this by thumb down, maybe? Okay, I don't see any thumbs down. So I assume everybody managed to upload, to download the data.
Oh, I think one person has it still downloading. So maybe we could give a minute just for maybe some slower internets.
Sounds
so
good.
It seems like many people have it
so
working.
I think that was actually one of the biggest challenges of the workshop, to download it. And then the second one we will face in a second is that everybody has MZmine running.
Oh, Zoom doesn't have a thumbs down, Daniel.
Oh.
Only thumbs up.
There is a no button as well, I think. Okay. I think there's a no symbol. Okay.
Okay, well, it seems like from the chat, most people have had success. So.
Okay. Cool. Then, yeah, let's move on to MZmine. And before I gonna just open the software on my computer, I just want to like give you like that little overview figure here. And oh yeah, like all the slides we're showing right now, they're all available in the Google Doc we shared with you, from which you got the Zoom information. So I assume that you should have access to that. So yeah, just feel free to download the PDF. And then yeah, I think in particular this slide here is kind of like very helpful because it shows you like a step-for-step recipe for feature finding with MZmine. And yeah, what we're gonna do now in the next half an hour is basically just like go through each of those items, and then we probably like can briefly discuss some of the very basic settings we're gonna use, and then yeah, we should end up with a feature table as .csv and an MS2 peak list as a .mgf file. All right, so let me go to MZmine. So yeah, I downloaded the latest version, and I basically got here a zipped archive file called MZmine 2.53 for Windows. So I hope all of you managed to download that. If not, as a very brief recap, if you Google MZmine and go to the MZmine GitHub, then here there's a download button, and it should directly bring you through that download page, and you can just like download Windows version or the Mac OS or Linux. So yeah, and once you downloaded that, you can extract that file, and then what you should get is basically a couple of files when you extract this in a folder. And what we need is here for Windows, .mzmine Windows batch file. And then I just double click, and that should launch the console here. And if everything goes planned, then that MZmine window here should pop up. So yeah, maybe to get some feedback, who managed to download that and has this open right now? Or maybe better reverse, who could not download this?
Oh, Daniel, maybe we could cover files have to be centroided before opening them in MZmine.
Yes. So yeah, that's a good point. Thanks. So when you convert your raw files to MZML or MZXML format, make sure to use the peak picking function in MS-Convert to get actually centroid files. The files we provided right now for the step-to-step tutorial, those are all centroid, so those are fine. But if you now try this later with your own files or from your own machine, make sure it's centroid format. We did not talk much about file conversion, so I mentioned it just a second ago. MS Convert is kind of like a very convenient tool. It's part of the Proteo Wizard package, so that's all open source available. We can also talk about that in the breakout rooms later if that is an issue. So I think for now we're like good on files, as the files we provided you are all centroid.
And there's also extensive documentation on conversion, file conversion. That's really useful.
All right, cool. So shall we move on with the step-to-step tutorial? So yeah, again, what I'm gonna do now is I'm basically gonna jump back and forth between here, the software on my computer.
Daniel, can you explain centroid versus profile?
Sure.
It's one of the questions.
Yeah, so profile mode is kind of like what I think most mass spectrometrists want when they acquire data, because it gives you basically every data point from a mass spectra that your machine records. And that means that you actually have like a kind of like real peak distribution of data points. So you have many data points per peak. In centroid mode now, you forget basically 99% of that information and just take one data point at exactly the apex of such a peak. So I wish I could draw this on a whiteboard here really quick, but yeah, for now you just have to live with my explanation. So it's kind of like a reduced information, and it only picks the apex of the peak, and then you really get only lines, so not a real like peak distribution as you probably know it from like chromatography also. That makes computational processing of that information way easier because it's less heavy. So files are like considerably smaller. That's like one way to like directly see if like a file is actually centroid or profile when the file size is like pretty big.
And there's a good link in the group chat that Laura Sanchez posted to illustrate the difference visually. It's useful.
Thanks, Laura. All right, so let's move on with the step for step then. So I'm just going to go quickly back to that one figure because yeah, as I said, I think this really like gives you like the recipe what we're going to do now for pre-processing in MZmine, and we obviously going to start with step 1, and that is data import into MZmine. So here it's still MZXML. You guys have MZML. That's basically the newer version, but still both file types are supported in MZmine. So if I go back now to MZmine, what I need to start with is kind of like, yeah, load this data into the software. And therefore, I'm going to go to raw data methods and then raw data import, which basically will bring me to, yeah, like a browser window. And now I can go to the place where I downloaded and saved those files. And yeah, so I hope you all remember where you downloaded those files. And then, yeah, I see basically here the fix MZML files, and I can directly mark all of them and then just hit open. And then it asks me to remove this prefix. I don't really want to remove that, so I say do not remove. And then, yeah, like the software should start doing things. So you see that there is some progress being made down there. It seemed to be slow, but now it's getting faster, and it's actually loading that information into MZmine. So now I see here on the left hand that under raw data files, I have like my different files, and I could now use visualization tools from actually MZmine and already like display like the chromatograms or like fancy 3D plots and kind of like investigate and explore this just on a visual fashion. But yeah, what we want to do here is really just like process them and yeah, create like a table of information out of it. So in case you can't resist and visualizing them, so just right click on it and then there would be a show TIC option or show 3D visualizer. So the MZmine has definitely a couple of like fancy tools for data visualization. Anyway, we're gonna stick to our plan here, and we just want to process this now for feature-based molecular networking. And then the second step after we loaded the raw data is that we need to basically define what's a peak and what's noise. And that's peak detection. So if I go back and go now to raw data methods and then go to feature detection, then there's this function mass detection, and that's basically just going through those files and like picks the most abundant peaks that are defined based on a threshold that we can now set. So, and that's actually already like a very crucial setting, because if you set that threshold too low, then your data will be full of noise and it's going to take like really long because there's a lot of information. And if you set it too high, then you eventually will miss like half of your features or like the really interesting stuff, which is like more low abundant. So, and this setting is also kind of like hard to predict because it's like depending on your
Daniel,
vendor platform. Yeah.
Oh, I think there has been a little confusion. Maybe you can just repeat that last step after you, or maybe you could just redo this step.
Yeah,
He
ask questions that if anybody that follow and is not able to follow, that they have some time.
Yeah. Thanks a lot for slowing me down. So it's a little bit hard with on Zoom because I can't see all faces in the room, and I don't see knocking or shaking heads. So yeah, thanks for bringing this up.
You can watch me because I'll be watching the chat and then I'll be shaking.
Sounds good. Also, I'd encourage everybody. So Zoom has like some basically live feedback options. So there's a go faster or go slower button, and there's a no button and a yes button. So yeah, if like it's like too fast or you don't get something, then feel free to like use some of those and indicate that. So yeah, just to recap, we basically loaded the data into MZmine. We went through raw data import, and then I selected those files and just hit open. And then they appeared here on the left. So everybody should be at that step now and basically see that the files are in MZmine available. And now the next step would be to basically set a peak threshold just for, like
actually, sorry, Daniel, to interrupt again. Where are those buttons on Zoom for the participants?
If you go to the participant list, then they're like on the bottom from it.
Okay, thank you.
Let me see if I can. So, do you see it now?
I see it, yeah.
And then
does everyone else see it?
Appear next to the.
Cool, got it. Thank you.
Yeah, we don't see it when you open up the participants list, but they can open the participants list and it's on the bottom.
Okay.
All right. So, okay, mass detection. So now we have the raw files loaded in MZmine. And now the next step would be to basically define that threshold. So therefore I go to raw data methods here in the drop down, and then to feature detection, and then to mass detection. So, and when I click this window pops up. And yeah, as I said, this is really critical because yeah, that depends on like the vendor platform you use, so that values can differ, right? So what's a good threshold? And I think the best way is actually to inspect your data and kind of like find that out. So, and to do that, we use here the mass detector centroid. And again, here it's really important that you have centroid data, otherwise that won't work very well. And then next to that centroid field here, there's a box. And when I click this, I can like basically define this noise level. And now, yeah, that is kind of like hard to know. I would say we can use 10 to the power of 6, which typically is like a very tough threshold for the Q-Exactive platform on which this data was acquired, but that might be different for your machine. So really here, the best way to deal with that is to check this preview button here, and then actually get like a look at the data you have and define this threshold based on that. And here I can now simply select one of those files. Let's say we use here one of the iron files. And then I can go to a random scan, let's say to 1279 within my chromatogram. And now I want to make sure that that's actually an MS1 scan. So here in this case, this would be MS2. You can see this here on the top. So if I go now one farther, then I can see, okay, that's an MS1 scan. And now with the threshold of 10 to the 6, every detected peak is displayed in red. So here, the major peak in that scan would be detected. And all the blue peaks here, they would not be detected. So in here, if we like zoom in, see there's the red ones are detected, but the blue ones not. And I think for this scan, this value here is probably already pretty much okay, because all of that kind of like noise here at the bottom is not detected, but like the major peaks are detected. So if I zoom back out. So yeah, I think for us, this would be now an acceptable value. And also it's kind of like more at the upper end, which will speed up the processing. But if I would lower this 10 to the 5, then you would see, okay, now I get most of the peaks, but not like all the threshold. But if I want to like look at really low abundant compounds, I might rather want to use that. If I would use 10 to the 4, then I would definitely get like everything. And that's exactly the scenario when like I would introduce here a lot of noise and many like features, and yeah, that would basically slow down the process. And if I had like 200 files, it would probably take forever. On the other hand, if I would use 10 to the 7, then almost none of those peaks would have been actually detected. So that's obviously too high. So for now, I'd say let's go with 10 to the 6. Okay, and then it's important that I define here a mass list. So by default, that would be just masses, but I actually like to give it a more meaningful name, like I don't know, metal, and then I use 1E6 for MS1, and then in a second, I'm also going to perform this for MS2 level, and we're probably going to use 1E3. So I define these thresholds here already in the name of the mass list. If I would do that more often, it would kind of like help me to keep track. And now I also have to make sure that I actually select all those raw files. So at the top, I say all raw data files, and then hit OK. And now you saw, okay, something happened for a second down here. And now all these files have a green check mark. So that means that the picking was performed, and that step is now done. So now, as we're not only dealing with MS1, but also with MS2 data, we of course have to apply a threshold for MS2 as well. So therefore, we're simply going to do the same thing again. We go to raw data methods, feature detection, mass detection, and now define a threshold for MS2 level. And that we do by simply changing the scan filter here. So if we set a filter, we can simply change MS level to 2. And then again, set the threshold. And here it's now really important that MS2 normally has like a lower signal level than MS1. And if we go to the preview and go now to a random MS2 scan, you will see that here, okay, with 10 to the 3.
Daniel, can you show the last bit again? Somebody just asked.
Sure. Okay, so we finished MS1 peak detection, and now we want to do MS2 peak detection. So we go to raw data methods, feature detection, mass detection, just the same as before. But now we want to change for MS2 level. So we change here that filter on that set filter button. And here under MS level, we change this to 2. Now you can see here, scans, it only considers MS2. And now we define a threshold for this. And again, I would encourage you to use, like the preview and kind of like look at like the peaks you would detect. So here with 10 to the 3, it detects most of the peaks. If I would use the same threshold as for MS1, that would not turn out very well. In this case, I would not detect any peak in that spectrum. So that's really a critical step to adjust the threshold for MS1 and MS2 like appropriately. Okay, so 10 to the 3 for the Q exactive is okay. And now it's also important that the name of the mass list is exactly the same as for the first step, because MZmine only builds from like that one mass list, and you want to have like the basically MS1 and MS2 organized in the same mass list. Okay, so now I hit OK again, and I actually made a mistake because I did not select all files. So I have to do that again. Here, I want to make sure that in the raw data files, all raw data files are selected.
Daniel, make sure that you go through the whole flow again so that people can follow you because the mistake that you made.
Yeah, so raw data methods, feature detection, mass detection, and then, yeah, so the settings are all okay. I just set them, and I want to make sure that at the raw data files, I actually select all raw data files. So I do not only perform this on one file, but at all at the same time. Okay. And now you could quickly see that it was actually performing it on all 6. Okay, so now we are done with the mass detection. And we're going to go to the next step. And that is chromatogram building. So now what we want to do is basically take all data points, first only from MS1 level, and connect them now to extracted ion chromatograms. So therefore, I go again to raw data methods, feature detection, and then ADAP chromatogram builder. So on some of the tutorials we had before, we used the just standard chromatogram builder, but as you can see here, that's not supported anymore. So I would encourage you to move on and use ADAP. So this has like a couple of other nice functions, which probably will also help you to reduce noise. So now here, the first step again, and this time I'm going to do it right away so I don't forget, is to select all raw data files. And then we want to build chromatograms on MS1 level. By default, that's already correct. And now I want to choose that mass list that I just created through the peak picking. And now I can define minimum numbers of scans that needs to be in a consecutive fashion, so that need to be after each other in order for a peak to be created. So this means that really like a certain mass needs to be observed in like 4 or 5, in this case 5, following scans in order for a peak to be actually established. If I would set this to, I don't know, 30 or something like high, and unless I have like an insane fast scan speed, probably most of the peaks would not be created because the peak was only above the threshold in probably a couple of scans. So in our case, I think 5 or 4 or something like that is appropriate. But yeah, again, this depends a little bit on your scan speed from your machine and also on your chromatography lengths. So the longer your gradient, the more likely is that you have wider peaks, and then this number can be higher. So now I want to set basically signal thresholds. So here I orient myself a little bit on the initial signal threshold. I just multiplied by 3. If we assume that basically our noise was at 10 to the 6, and we would define limit of detection as 3 times the noise, then this would be 3d6. And then the same for the minimum height. And then my mass tolerance basically gives the tolerance of like peaks to deviate between those scans. And that's another very crucial setting. And you should be aware of basically the performance and characteristics of your machine and know whether that's high resolution or that's like more like a low resolution machine, like a quadrupole or an ion trap, and then set those appropriately. It's interesting because you can set 2 values here, either absolute in MZ or relative in ppm, which is probably more appropriate for the high resolution users here. So for the Q exactive with external calibration, I would assume that we have at least 10 ppm mass accuracy. So that would be an appropriate setting here. But let's say this was a quadrupole, then I probably would rather go to something to like 0.5 MZ, which would correspond to I don't know, like a couple of hundred or thousand ppm. So yeah, you should know this basically based on the platform you're using. If you don't know, ask the mass spec people in your lab who are most familiar with that type of equipment. I can define two values here. If I would put like a large value here, it automatically takes the larger number.
Size larger? I agree, it's really small on this end.
Say what?
So someone asked to make the screen size larger, but I think in MZmine, I don't, yeah, maybe you can just make the window bigger, but I don't think the fonts actually get
maybe
bigger. Or
change the resolution of your screen. Screen is not clear.
I can do that. I hope it won't.
But a participant had a good point. All of this is also covered in the slides. So if anyone gets sort of lost, everything that Daniel's going through is on the slides as well.
Yeah, I don't really want to change that because I think it's going to also mess up the recording. Yeah, is it impossible to read or is it just difficult to read?
It's just tiny.
All right. Yeah, I would, if it's okay, I would just move on like that. Apologies for MZmine having small.
Somebody said you can zoom in the window too.
All right.
It's for us, it's like between probably 4 and 5 font. So it's smaller than the small text that you see in the Nature paper. In the legends.
Yeah. I mean, okay. Shall I try to change my screen resolution?
Yes. So somebody said if you go to the top of the Zoom screen, click options and moving closer, and then you can zoom in. Yeah, this looks way better.
Is that better? All right.
Yep. Thanks.
Okay, so now back to mass accuracy. Again, that needs to be like really appropriate set for the type of like machine you use. So again, for the QXactive and Orbitrap analyzer, in our case, 10 ppm is appropriate. It's also like more on the wider side. So I could probably also go down to 5 ppm, or if I have internal calibration, probably close to 2 or even 1 ppm. But I think for the workshop purpose here, 10 will be fine.
Hey Daniel, so can you clarify which level this is on? Because there's been some confusion.
Yes, this is MS1 level.
Yeah, thank you.
So,
and that's indicated just by here.
Yeah, basically,
I guess you're sharing your screen,
MS1 level 1.
Yeah.
Also, so just from a logical process for, standard DDA, so data dependent acquisition, MS2 data, you cannot really build peak lists on MS2 level.
Yeah.
So you need to like build your extracted ion chromatograms on MS1.
Thank you.
Okay. So then we hit OK, and you should be seeing that something actually happened. So again, down here in the task part, like something was processing, and now, we see that in under feature lists here on the right-hand side, we now have 6 different peak tables. And if you are really interested in how that looks, you can already click on one of those. And
so
then you will
the question is, why did you choose threshold of ADAP higher than the noise level?
Because I think like a standard definition of chromatographic peak is that the limit of detection should be like around 2 or 3 times of the basic noise level. So yeah, I just want to like be like a little bit more strict for actually the construction of peaks than for picking of peaks from MS1.
And then how do we determine minimum group size in the number of scans?
Yeah, again, that's a very good question. So if we go back to ADIP, so that's this value here, minimum group size is of number of scans. And oh yeah, that's also good information. If you hover above those fields, actually like a help field will pop up and explain you a little bit about that particular setting. And in this case, it's basically the number of scans in which a certain mass needs to be present that are after each other in order for a peak to be created. So, and that is, I think that's a really nice function in ADAP in comparison to the like older Chromatogram Builder, because that really helps you to reduce noise. And like if you think about noise in a mass spectrum, it's probably like a certain mass that will appear randomly in like one scan, but it's very unlikely that a noise signal would appear in 5 consecutive scans after each other. And that basically setting helps like to remove like, yeah, such like noise by, yeah, putting this restriction that actually masses need to be present in 5 times after each other. So, and how to set this?
Another good question is if different collision energies are used for each precursor mass, would different scans be considered in minimum group size numbers of scans?
Yeah, so collision energy should not fall under that at all, unless you did some type of like all ion fragmentation, because that's on MS level 1. So yeah, I would assume that.
Then there's a question: what parameters do you suggest for ADAP with Orbitrap instruments? Well, this is Orbitrap instruments.
Yeah, so it depends a little. So from as a user, I know that like LTQ Orbitraps typically have like a little bit lower signal level. So that can like vary by like an order of magnitude. So if that would be acquired on an, I don't know, LTQ Orbitrap Elite, then I probably would use 10 to the 5. But it might also vary a little bit with like a particular machine in your lab. So really make sure to like look at the data and like decide on that setting based on the data you have. Okay. Thanks a lot for bringing those up, Peter. Also, later we will have breakout rooms. So if you have like any questions which are not directly related to this year, feel free to ask us later in the smaller groups, which can be a more interactive chatting.
Oh,
all right. So now
one more question. Someone was wondering if there's any way to go back and make a correction in the parameters after hitting OK.
Yes. Yes. And that is really like the nice way. What I love about MZmine is that you kind of like can go back to each step in that mode and just like start from scratch. So if I'm not happy with what I just did, I simply go back to raw data methods, feature detection, and then ADAP, right? And now I can just like write a new list of peaks. For example, let's say we want to be more strict with the group intensity threshold, and I want to use 10 to the 7. Now I can just redo that, and then you see that there's like a suffix, so that automatically like names this, and then I can just indicate that I actually want this to be named 1E7 because I changed this one setting here. And if I select now all raw data files and hit OK, then you will see that there's simply now a new set of peak lists be written, which obviously have now the more stringent setting, and now I can like move on from there. So this way, I think like to like really tune the settings and like explore your data, that tool is like very nice because it's very interactive and you can like go back to different points. The thing is, if I have multiple peak lists here, now I just need to be more careful when I select them and move on to the next step, so I do not do this processing step for like all feature lists at once. But I will get into that in a second. So now, yeah, again, we have our chromatogram lists. And if you double click on one of those, such a table here will pop up. And you can see already like the first type of information you have. So here is basically MZ and retention time. And then you see like that peak shape here, which we can like make a little wider. And then there's a height and a peak area. And so for the chromatography specialists under you, you will see already that some of those peaks look very appealing, and some.
So Daniel, was a question in the previous when you look at the files on the right, not this window, but the files on the right, when you do the processing, yes. How can you check what parameters were chosen?
This you can't really. That's why I like to define the thresholds in the name of the mass list. Okay. So if I would go back now and want to like repick the masses through feature detection, mass detection, and I want to change a setting here, I would make sure to like change that name. So, but that's kind of like as a personal thing, how I keep track of it. So there might be other ways. Okay.
Thanks, that's perfect.
Going back to the peak list. So how I got there was I simply double clicked on one of those, and yeah, you can basically see those peak shapes. And yeah, now some of them at the end of the gradient look like noise or like some type of like contamination. Some peaks have like kind of like a hump, especially with dissolved organic matter. That's unfortunately a peak shape we observe quite regular. And then let me find some nice examples. You will also see examples like that where we actually have two peaks, right? And that's nothing surprising. That are simply like isobars. So two chromatographic resolved peaks that have the same mass. So, and to like basically toss them apart and consider them as separate features, what we now have to do in the next step, when we go to our list here, is chromatogram deconvolution. So this basically now only considers actual peaks and not like the full extracted ion chromatogram. So in this case here, we would have like two peaks, the smaller one here on the left and the bigger one on the right. And what I want to do is basically define them and then separate them into actual chromatographic features. And therefore, so now I have to be careful because I only want to process like that one set of the list. So I mark them all by, you know, just clicking, and then with Shift, I can select all of them. And then I go to now feature list methods, and then feature detection, and then chromatogram deconvolution. So, and now a new window pops up. And now you can see that at the top, I can, for feature lists, select either all feature lists, specific feature lists, or those created by previous steps. But what I want is as selected in main window. So it really only keeps now processing the 6 ones that I selected here. Then I can also specify a suffix here, deconvoluted. If I want to like play around with like multiple algorithms, I could give this a more meaningful name, like, I don't know, baseline cutoff. So because that's the one we're going to use now. And then I can choose the algorithm. And here you will see when you click on this that there's actually many different like possibilities. So there's wavelets from XCMS or another ADAP wavelets version. And then there's like others like local minimum search, which I personally really do like because I think it's fast and efficient. And then there's also very like crude type of algorithms like baseline cutoff, which is probably like the most simple one. But for now, I want this one because I think it's very easy to set up. Because when you go to the settings for the baseline cutoff, you will see that there's only a few settings. And this is minimum peak height, which kind of like corresponds already to what we said before for the chromatogram building, and then baseline level, which kind of corresponds to our initial signal threshold for MS1. And then in addition to that, we have peak duration, which I would assume we have a 10-minute gradient. So we maybe assume that like the widest peaks are probably 3 minutes, and we have UHPLC, so they might be really sharp. So let's say 0.5 minutes, something like that. Again, this depends on the chromatography you use. If I would have like a 200-minute super long gradient with really wide peaks, then I probably would want to make this a little bit wider, like, I don't know, maybe 10 minutes or something like that. So that needs to be appropriate. But again, the best way to figure that out is actually to go to your data and check what's going on. And there's this show preview button. And that basically now gives you the option to have a preview of all the peak lists we have with that settings we set. And now you will see, okay, with that like, yeah, kind of like narrow window here and that settings, it will detect here just like wide peak at the end, but not that kind of like spiky stuff here at the beginning. Neither of those are like very like good peaks in my opinion, so I'm probably gonna rather go to something that looks more like a real peak to me. And then I would see that in this case here, this peak is actually detected because it appears down here. And if I would now, I don't know, make this too wide, then you would see that it's not detected anymore. So that's a good way how to check. And we can now basically scroll through a couple of examples. And obviously this one here was not really challenging. Let's go to one where we actually have two. Oh yeah, this is a beautiful example. So here we have, I would say, at least 3 different peaks that are clearly resolved, but the baseline cutoff is not capable of like separating those 2 peaks. And the reason is that they're not baseline separated. So although we have a clear separation, the signal never goes below the baseline, and hence the baseline cutoff, which basically just like draws like a line at the baseline noise level, it does not recognize that. So if I quickly note this down, so that would be.
Hey Daniel, maybe we can show them an example of like doing local minimum search as well.
Yeah, that's exactly what I want to do now.
Yeah, I guess one of the reasons we went with this was just because it's sort of the simplest and the quickest.
Yes.
So for people unfamiliar, it's sort of just, yeah, the quickest. But so I guess since we usually do use the other ones,
yeah,
maybe we can just take them through that.
If I would just hit cancel now and go back to that window, and now instead would select local minimum search, you know, and you will see that there's way more settings now. So that's why it's a little bit harder. And if you want to start, and that's the first time, maybe try first the baseline cutoff, but then once you become more familiar with it, maybe this might be more appropriate. And if I go now to exactly the same feature, which was number 37, I think. Yeah, so now I can put like, I don't know, some settings here. And then you will see, ta-da, ta-da, I actually get those features split. So what the local minimum search does, it simply has like a sliding window, which is here defined through like that search minimum in RT range. And it now looks basically for slope. And once there's like a local minimum defined, it just like draws the line there.
So Daniel, maybe now that we went through this local minimum search, we could kind of go through it again a little more slowly, I guess, since there are more settings. I think we did lose some people now.
Okay, I mean, I'm probably gonna go back and proceed with the baseline cutoff. I think that was just like actually an example that there's different options, and it's hard to say, yeah, that's the right thing or that's the wrong thing. So I think the best way is to actually explore your data and try and understand what the different things do. Right?
Yeah,
so in this case,
I would say
for
also
the chromatographic
like
threshold.
Yeah, because a lot of people are asking for like ideal thresholds and things, but I think it's, as Daniel said, it's really important to kind of look for examples like this one and see how the different thresholds work, because yeah, it'll be important, of course, to kind of resolve each of those peaks. And so by like playing around with the thresholds, you'll see sort of which work the best for your data.
All right.
There's not really a one size fits all, I would say.
Exactly. So yeah, what I would recommend you is, again, start hovering above those fields. And then yeah, here basically you can just like apply a general like relative like signal noise in each chromatogram. That can be obviously like smaller as well. In this case, it worked. Then the search minimum thing, that's depending on your chromatography length. So if you have like a longer run, again, you probably want to like make that window a little bit larger, or if it's faster chromatography, then you want to make it like shorter. Then minimum relative height is basically goes like a little bit ahead as the chromatographic threshold. So that means that like the smallest peak detected needs to be at least 10% of the largest, right? So if I would make this bigger, then you would see now that small one here is not detected anymore. So I think probably 10 is appropriate. Then absolute height, that kind of like corresponds to just like the initial threshold. So obviously it does not make sense to make it smaller than your initial threshold. So 3e to the 6 would be fine. And then a very crucial setting is the minimum ratio of peak top to edge. So this kind of like defines the slope. So the smaller the value, the sharper the peak needs to be. And if you see when I change this, okay, in this example, it actually does not do much. But if you have like more problematic peaks and wider peaks, then that value can be pretty critical. I typically use settings between 1 and 2, but I would encourage you to, go through a couple of examples and then see if that works. Okay, so here with 10, we're not doing good. With 1, it seems to work. 1.5, yeah, but it's not ideal because you can see there's a shoulder, which I do not get right now. So
real quick, just to interrupt, if you want to read more about each of the different parameters that you can set, there's also a help button at the bottom. Can you just highlight that real quick? Yeah, which kind of goes through sometimes in a bit more detail. Other times it's about the same amount of detail, but that could be helpful.
Yeah, good point. Thanks for bringing this up, Allegra. So yeah, there's also on the MZmine side extensive documentation, which can be accessed through this help button here. And then you can like, yeah, basically give it a read and try to understand what those settings do. So for us to like, yeah, move on with the workshop and get to our final like output to actually do feature-based molecular networking, I'd say let's use the baseline cutoff for now. Very simple. And then, yeah, I think something like this here, 3E6, then peak duration 0.05 to 2 minutes, and a baseline level of 1E6. I think that should be appropriate. And then, in addition to that, this is now the central step where we pair the extracted ion chromatograms and MS2 scans. And this is super critical because otherwise we don't have like that link, which is needed for the molecular networking down the line. And to make this, establish these links, we just need to check these boxes here. MZ range for MS2 scan pairing, and yeah, this is only absolute values. So again, this corresponds a little bit to the resolution of your machine. So for high res, I would use 0.01. And for low res, probably more something like 1. And then also chromatography. So basically, what's like the widest window you assume an MS2 to be triggered within your peak. And it's also hard to like have like one value for all different types of peaks. But I think for our type of chromatography, something like 0.2 minutes is probably appropriate. So yeah, and then I just hit OK. And then you can see that now 6 new peak lists have been established. And when I open one of those, I should now be able to see that hopefully most of the peaks here, most of the peak lists have only one peak. Yeah, there's some, yeah, exactly. Like this one here, where actually like the deconvolution failed. But yeah, we won't find a setting that is perfect for all molecules we have. So here it's really like try to get it as good as you can, but it's like don't expect that it's going to be perfect.
Daniel, there's a question for when we're using different collision energies. Then are all of the MS2s paired to the MS1 or only one of them?
Yes. I think like a way to differentiate between different collision energies, if you would have that, is that you could separate them at the beginning before the feature finding. But that would be probably like an advanced type of like processing here. So in raw data methods, I think there's some filtering options. And I don't know if you can filter there by collision energy. We can follow up on that later in the breakout room, as this is like something more advanced, I think. All right, so coming back to our deconvoluted peak lists, again, if I double click on one and open this back up, I can see like all the features in this particular sample, and we now have around 200 per sample. It's like not too many. And if I click now here on the header MZ, then it sorts automatically those peak lists by mass, or I could also do that by retention time. So yeah. And interestingly, if we do that by mass, what you will see is that many of the peaks have exactly the same shape, right? So here, for example, 240, 241, 242, and that is like not surprising at all, because most likely 241 and 242 are simply the stable isotopes from 240, right? So these are like kind of like not really redundant, but that are kind of like, yeah, multiple features that belong to the same molecule. And yeah, I think we can use this to our advantage later on, but like for now, what I want to do is I actually want to collapse those features to the same one. And that in our recipe would correspond to isotope grouping, step 5. So again, I want to highlight now only the peak lists with which I want to like proceed. And then I go to feature list methods, and then there's isotopes, and then there is isotope peak grouper. So and now a new window will pop up, and I can select the feature lists here. I want to have as selected as window, and now it's very much like the same type of settings as we had to choose before, and that is mass tolerance and retention time tolerance to basically look, okay, does a peak within a certain window actually correspond to a delta of 13 C isotopes? And yeah, in our case, I just want to define this here as ppm, 10 ppm again, and then use probably like the same type of retention time tolerance as before, maybe a little bit narrower than for the MS2 pairing. So here, 0.1 might be appropriate. Could also be smaller, but I think for us this is good for now. And then I have a couple of other options, and that becomes especially interesting if I would deal with peptides or proteins where I have multiple charged species. And this is here maximum charge. And that basically is important because if I would have Z of like 2, then obviously the mass difference between my monoisotopic peak and the first 13C isotope would not be 1, but it would be 0.5 because it's mass over charge, right? So I want to like define this. I think in our case, we may have some doubly charged molecules, but probably not multiple charged other species. So I'll leave that just for 2. And then also for isotopes, I can now select whether I want to like pick the most intense or actually the lowest MZ. So, and that becomes especially interesting when you deal with halogenated compounds that have like a more weird isotope pattern where maybe like not the smallest, not the biggest peak is like the monoisotopic, but rather like the smallest peak. Right. So, and then I think that's pretty much it for this setting. So then I would, yeah, just like go ahead and click OK. Oops. And then I should see that now new 6 peak lists appear here in my window. And now, yeah, they have the suffix deisotoped. And when I click on one of them and sort this by MZ, then I should hopefully not observe like peaks with the same shape and like offsets of 1. So, and as far as I can tell, oh, here it actually seemed to have missed 1, but not the first isotope peak, but rather the second. So maybe here was like a more wider mass window, it would do a better job. But I think roughly that looks kind of like acceptable. Okay, so now if we look back at our recipe here, we now are at isotope grouping. And what we need to do now is, because they're all in the same, yeah, so like basically all samples are still like separate as like different peak lists. I want to now align them between each other to actually come to a, yeah, like a feature matrix and have kind of like the same peak with, yeah, like the sample specific peak areas, then like, yeah, collapsed in one version. So to do that, I again, like simply select the ones I want to proceed with. So those would be all the deisotope ones, and then go to feature list methods, and then alignment, and then use the join aligner. So, and again, here we have mainly MZ settings, which will be the same as before. And then retention time, which should be also the same as before. If you have a larger batch of samples, you may want to like give some tolerance, because obviously the potential retention time drift from your first to your very last sample could be like higher than the retention time drift between like 2 isotopes within the same run. Anyway, I think for here 0.1, that's still appropriate. And now we can also put like a weight on MZ over retention time. I personally believe more in like the MZ than retention time, so I would probably do like 75-25, but that might change if you have a different type of like mass spec or different type of chromatography. And yeah, the other boxes I for now leave all unchecked, and then I just hit OK. And now what I should get is here an aligned feature list. And when I double click on that, you can now actually see that that peak shape here now has multiple colors. So that means that multiple samples contribute now an XIC to that particular feature. And now I can also scroll here to the right, and then you will see that there's actually multiple samples now present. And in the first example, you know, I everywhere have like a green dot. So that means that that particular feature with the mask 365 and 4.36 minutes retention time was actually present in all of my samples. And that's already like a very good way to kind of like look at presence and absence, because you will see now some of them have a red dot, like this one here. So that feature, that particular feature was not detected here in HUI N3, which could mean that it was simply not present in that sample. But as we deal with some replicates here, it could also mean that simply our settings were not capable of like detecting the feature in that particular sample, because maybe it was like a little bit lower abundant, or maybe there was some other like ion suppression or co-eluting, other things that changed that peak shape. So, and what we can do now to kind of like find such missed features is gap filling. And yeah, if we go back to our recipe, we see, okay, there's the gap filling function here at 0.8, and then, oh, there's actually also 6 and 7, and this is isotope filter and MS row filter. And those become especially important to do before gap filling if you have like a large data set. So with our few samples here, I could do gap filling right away, but because that's kind of like a time consuming and like resource consuming job, it might make sense to actually remove some of like the noise features before you do that. So I'm gonna close this now for a second and go back to my peak list. Now I'm just gonna quickly show you how to do actually that filtering. So therefore we select aligned feature lists and then go to feature list methods and then go to filtering. And then there's this function peak list row filter or feature list row filter. And here I typically use simply 2 options. That's minimum peaks in a row. So this is helpful when you say I have like a couple of replicates. I want a peak to be at least detected in, let's say, 2 out of 3 replicates. And then I have isotope filter, which makes use of that collapsed isotope patterns. And here I can simply say, okay, I only believe a feature to be real if it has an isotope peak, and it needs to be at least 1 or maybe 2. So that's kind of like depending on how stringent I want to be. And now one important thing is that there's also the option to keep only peaks with an assigned MS2 scan. And this is particularly interesting if you want to do feature-based molecular networking with GNPS, because that basically cuts off all MS1 peak lists if they do not have an MS2 scan assigned. If you're like really exploratory and you want to really report everything, also stuff which did not make it in your DDA to actually trigger an MS2, you can leave that unchecked. But for us, I would say, let's use this for now. So I basically use minimum peaks in a row, 2, minimum isotope peaks, 2, and then the MS2 filter. And I just hit OK. And now I get like a filtered peak list. And that one should typically, if we look at it, contain less features. So let's see. Here we have, when we go to feature list info, we have a total of 74, whereas before filtering, we had actually 400. So that filter really like reduces like the number of features, and hopefully reduces mainly noise, but it may also reduce some valuable stuff. So here, I think also it's good to play around with this and find appropriate filter settings for your sample. But
hey, Daniel,
yeah,
there's 2 questions. So the first is that, so we've already done de-isotoping. So someone is wondering why we set minimum isotope peaks to 2.
That actually makes use of that isotope grouping. So that did not group isotopes, but it only allowed features that had 2 isotopes in there.
And then someone wonders if we can use MZmine for DIA.
Yes, I think there is a deconvolution algorithm with ADAPT as well, but that would be definitely also something for the breakout session, especially as we are running a little late and I want to finish this now so we get our MGF file and CSV file because we are almost there. All right, so we have to filter the peak list. So now I would just quickly do gap filling under feature list methods, gap filling, peak finder, and then use kind of like the same settings as before in terms of intensity tolerance, yeah, mass accuracy and retention time accuracy. Just okay. And now we have an aligned feature list that is gap filled. And this is already now our final product. So yeah, again, you can like scroll through this and could also manually remove some of those features if you're like unhappy with them, which I don't really like because it's hard for me to reproduce my manual curation. So I rather report all of them. But if there's obviously something really bad, then yeah, you can in theory remove that. You would just basically hit delete selected row. Generally, I would encourage you to probably not do that, but you could if you want. But now what you want to do in order to submit that job tomorrow for feature-based molecular networking and GNPS is to select that final list and go to feature list methods and then go to export import. And there is export submit to GNPS feature-based molecular networking, FBMN. So you just select this, and then you can here first, select the feature list as selected in main window, and then I can here define a file name, which ideally should be in the same folder as before.
Daniel, maybe when we're done with this, we can just real quick go through gap filling again. And also maybe we could talk about like, what are some of the benefits of gap filling and like why would we want to do it versus not want to do it with different data sets, maybe? That could be helpful.
Yes. Okay. It doesn't want me to save it. So I probably need to select already an existing file here. Okay. So yeah, that's actually probably not so awesome. Okay, and then once I select here an MGF file, then I can select the peak list I had before. And then for now, I would just leave it like that. You can see a couple of other options, but in this case, I only want to define file name, mass list, and then only export, again, filter like rows with MS2, which kind of like all of our rows have only MS2 anyway, because we had that as a filter. And then I hit OK, and then it should write a couple of files. And in this case, when I go to my workshop here, then yeah, I should basically see that there is a CSV file with quant, and then there should be an MGF file with the MS2 information. So, and this is mainly all you need for tomorrow. If you did not make it till there, that's not a problem at all, because in that massive data set we're going to share with you, all those files are already pre-processed for you. So we can basically just start from there tomorrow. All right. So shall we go quickly back and iterate the gap filling for a second and then go to the breakout rooms, or?
Yeah, I think that might be helpful to go through gap filling again.
Yeah. Okay, so that was basically just like the last step. And if you look at our, yeah, like recipe here.
Oh, maybe we can just go through gap filling and the export just through the end one more time.
All right.
Sorry, I think that would be helpful.
Okay, so we basically restart in here, and that's, again, the beauty was MZmine. I can basically go back to any step in my processing history because all those peak lists and aligned feature lists are still like present here. So to do gap filling, I would basically just highlight now the filtered peak list, go to feature list methods, and then go to gap filling and go to peak finder. And now what this module does is it basically uses existing peaks from all the other peak lists and kind of like reiterate in the samples where a certain feature was not found with kind of like a relaxed setting. So in this case, I would simply apply the intensity tolerance was like 10% or something like that. And then MZ tolerance and retention time tolerance accordingly to the other settings I used before. So in this case, 10 ppm and 0.1 minutes. And I want to now name this, I don't know, 2. And then, yeah, if I submit this, you would see that there's now a new aligned feature list filtered gap filled. That now, again, would be like my final product here. And I want to support, export this now to an MGF file and an CSV file. So I go to, I highlight this here, then I go to export, and then I go to export to GNPS. And let's remove this here real quick. So I want to first define a file name. So yeah, here I could basically use that MGF file I already created, or I can like define a new one. Therefore, I go here on this points and browse to like a folder. Okay, it appears that you cannot create a new file here, which I think is a bug in the latest MZmine release. So what I would need to do is in that folder where I just was, so this test folder here, I will create simply a text document, which I call test MGF.
Daniel, do you want to go through maybe what is the function of merge MSMS, since it's like a newer development, I guess?
I mean, we can talk about that.
Or we don't have to,
session, but I think we're like really getting close.
Oh, I guess, sorry.
Thing. So. Seems it doesn't want to take it. All right, so in that case, I will just overwrite again another existing file. Sorry for that inconvenience. We probably need to fix that on the MZmine side. Okay, so it's defined here. Yeah, if you will have problems with that at home for your own data set, what I would recommend you is simply throw in a dummy MGF file for now, and then just like select this here and override it. And hopefully with the next MZmine release, that issue will be solved. Okay, and then here as a mass list, you will select that mass list we defined before. And then as Allegra just mentioned, there is a couple of other options like merge MS, which is kind of like an experimental setting. So for now, I would leave that unchecked and just hit OK. And then you should see that there are some files being written, and that contains of an MGF file and a quant CSV file. And those are the two inputs we will need tomorrow. And as I said, we will provide you that files. So independently, if you made it till there today, or for people who could not attend today, we will basically provide that material for part 2 of the workshop. And I think for now, that's it with the MZmine step-to-step tutorial. And I would say let's go to breakout rooms and have like more informal discussions. Ming, do you want to manage them?
Oh, that was,
Should
yeah.
I create them?
You can go ahead and create them. Just a second, because we'll probably wrap up after the breakout rooms anyway. So that was a great presentation, very detailed, and there's a lot of individual parameters. So that's, you know, it's both empowering and also kind of a slog to actually get your data ready for it. Some of the stuff we're doing at GNPS are trying to automate these kinds of processes. So within the lab, we have some presets for batch files that you can take a look at to build off of instead of building it from scratch. Again, these are presets that depend on the instrument as well as the data, as well as the data set size. So again, it's not a one-size-fits-all, and we're starting to integrate it all into GNPS. So if you want to try that out, let us know. That's all in beta, and it's on the tool index. But beyond that, we're also working on auto-tuning these things. So hopefully it'll get easier in the future. But as it is right now, in terms of being realistic, there's nothing that really replaces you spot checking it. But I'm a computer scientist, and I don't want you to ever do any work. So that's kind of a look ahead. But anyway, we will, Danny will organize the breakout sessions and happy to answer any questions.